Hi everyone. In this video, I want to show you how to use the inverse modeling or automatic inverse modeling capability of OpenHydroQual. So the problem I'm gonna consider is basically a chemical species or a pollutant undergoing a first order reaction. I'll try to basically use some observed data to estimate the first order reaction rate coefficient and also the initial concentration. Now you can use the techniques that I'm going to use, or the things that I'm going to use for this example. You can use it in for any other uh, inverse problem, including things related to hydraulics or uh, a lot of other things. So basically, I'm gonna start from basically I'm gonna use this reactor plugin. I'm gonna use a reactor for my model. So I'm gonna go to File, Add Plugin, and then I'll add this mass transfer uh, plugin, which contains a reactor. So let me just add that. So basically the plugin is added. So now I have this reactor, right? So I'm going to add a reactor. So this is it. It's a batch reactor. The problem is going to be very simple. So okay, so the next thing what I'm going to do is that I'll add a chemical species or chemical constituent. So I'm going to click on the chemical constituent icon. Let's call this constituent, I don't know, I'm going to call it A. Okay. Then what I will have to do is to define my reaction. So in order to define my reaction, what I'm going to do is that I will uh, basically I add a reaction parameter. So the reaction parameter is here. I'm going to call this first order decay rate. I'm going to call it KD. And let's just assign a value of 1 to it. So I'm going to assign a value of 1 for now. I'll change that later because I have to make this a parameter, an unknown parameter. Uh, then I need to add my reaction. So I'm going to go to click on the chemical reaction item. So I added a chemical reaction. So I have this one. Let's call this decay. So the name is decay. Now I need to specify a stoichiometric constant and a rate expression. The rate expression, as I said, I'm going to assume that it's a first order reaction. You can choose any other maybe more complicated nonlinear rate expressions and so on, with that may have more parameters. But in this case, I'm just going to do a simple first order reaction. So I'm going to type KD times A, and that means the rate of reaction is actually KD times A. I'll make the stoichiometric coefficient for A minus 1, and that means that it's being consumed, it's being decayed. Okay. So then next, what I will have to do is I'll have to assign, let's say, an initial concentration. So let's say, I click on the reactor, which is called reactor 1, and then for the property A colon concentration, I'm going to enter, I don't know, maybe 2 grams per cubic meters. And that's it. So my model is complete. I'm going to just run the model in forward mode to see what happens. So let me save this model. I'm going to save it to, I'm going to call this inverse test. So I'm going to save it here. And basically one more thing that I'm going to do by default, the duration of the simulation is only 1 day. I'll make this more. I'll make this 2 days. Okay, so let's go to general settings, and for the simulation end time, I'm going to right click on the property in front of simulation end time and then insert a numerical format, because otherwise it'll basically require me to enter a date time, which I don't want. So I'm going to say insert a numerical format, and then I'm going to enter 2. So now the duration of simulation is 2 days. Now let me just run the model. I'm going to run it. It's done. And then I can look at things like, for example, oops, something is not working. Oh, the reason is, I'm sorry, the reason is that the initial storage, I need to provide a storage for my reactor, or how much water is in it, and I forgot to do that. So now I'm gonna do it. So the initial storage is, let's say, 1 cubic meters. And now I can look at concentration. So this is the concentration. As you can see, we have the first order decay. Now, in order to do the inverse modeling, I will have to um, introduce some observations and then some parameters, and then assign the parameters to the right quantities of my model. So first, let's do the observation. So I'm going to add an observation. So this icon adds an observation to my model, the eye. So I'm going to click on that one, and then let's just assign the properties to the observations. So the object is going to be my reactor 1. Let's call the observation just observed concentration. Then I will, so the expression is going to be A concentration. So that's what we are measuring. We're measuring concentration of A. And so I have some observed data that I've prepared before. I'm going to now click on observed data time series property, or the value in front of observed data time series property, and I'm going to choose the observed data that I've basically prepared before. It's called observed data for inverse EX. I'm going to include the link to this to the comments of the YouTube video so that you can see it, but for your own application you have to provide your own data, of course. So I'm going to add this one. Now I can look at it, see how it looks like. So I can right click on the value, and then I can do plot, and as you can see, this is the data I have. So as you can see, there are some oscillations, ups and down, as usually that they exist for observed data. It may be due to, I don't know, measurement errors, or heterogeneity, or anything. So so that's my observed data. Then what I'm going to do is that I will now add 2 parameters. I assume that I don't know the initial concentration, and I don't know the decay rate, basically. Now, just to point out, I have produced the observed data that you just saw. I have synthetically produced them by assuming an initial concentration of 1 and a decay rate of 0.8 per day. And then I added some noise to it. So then so what I'm gonna do is, let's just add a parameter. So this so the parameter, this adds a parameter, and this is different than the reaction parameter. The reaction parameters are parameters that go into reactions. A parameter is something that we want to estimate. So keep in mind that they are different things. So I'm gonna click on the parameter icon. So I add a parameter. Now I'm gonna call this parameter. The name should be different than the KD. So I'm gonna call this KD underscore parameter to basically indicate that it's different than my reaction parameter KD, even though the values are basically related to each other. And then keep in mind that we can't use the same name of objects for two objects in OpenHydroQual. So the value, I'm gonna just, for now, I'm gonna assign a value of 1, and then I need to provide a lower and upper limit. So now I know that the observed data was generated based on a decay rate of 0.8. So I'm just gonna pick a range that is kind of contains 0.8. So I'm gonna go with the upper limit of 1 point, let's say, or actually let's say 2, and then a lower limit of maybe 0.5. Okay, and then I'm gonna keep the prior distribution normal. So and this has some effects. This actually impose a prior distribution, a normal prior distribution based on a 95% credible interval of 0.5 and 2. So basically the ranges will have an impact on the estimated value. But I think this estimated value is wide enough that the impact is minimal. Then, so that's one parameter. The second parameter that I'm going to add is going to be the initial concentration. So I'm going to add another parameter, and this is let's call this initial concentration. Let me expand this so that you can see what I'm doing. The value, I'm just going to assign the value of 2. Then the upper limit, I'm going to make it, let's say 2, and the lower limit, I'm going to make it again let's say 0.4. So this is the range that the inverse algorithm will search within. Okay, so now I have two parameters. Now what I want to do is that I want to assign these two parameters. I want to say what these two parameters represent. So in order to do that, I'm just going to click on my reactor first. First, I will do the initial concentration. So for the when you see the initial A concentration, I'm going to replace this 2 by my initial concentration parameter. So I'm going to right click on the name of the property A concentration, and then this menu parameters will come up, and then I'll say it's actually take the value of concentration of A, or initial concentration of A, from this parameter called initial concentration, right? So, and then the second thing, I want to apply my decay rate to the reaction, the decay rate parameter to the reaction. So basically, I'll go to reaction parameters. I have this KD. The value, I don't want it to be 1, but I want it to be equal to the KD underscore parameter that I just defined. So I'm going to right click on the value, go to parameters, and then I'm going to pick KD parameter. Okay, now I think everything is set. Let me save my model. So first I'm going to run the model in forward mode. Now, if you remember, I assigned some values to the parameters. So I assigned a value of 1 to KD parameter, and I assigned a value of 2 to initial concentration. If I run the model in forward mode, those are the values that will be used. So I'm going to run. Now let's look at, I can go to my observation. If I right click on the observed concentration item and go to results, I'll see 2 items. One is expression and one is observed data. The expression is the model output. So if I click on the model output, you'll see that this is my model prediction. So it starts from a concentration of 2 because my initial concentration was 2, and then it goes down. The observed data is actually my observed data. And one thing I can do is that I can copy this and paste it on my model predictions, and then I'll see how they compare. And as you can see, they don't compare very well because of course, the value of the parameters that I assigned was arbitrary. So now what I want to do is that I want to do an inverse modeling. So in order to do an inverse modeling, all you have to do is to click on this icon, which shows this 1 over x and then the play triangle. So I'm going to click on that one. You got to wait a little bit. This is a simple problem, so it's actually solved pretty quickly. What this graph shows is the fitness that is calculated, which is actually the difference between squared difference between modeled and measured data. And then as the code uses genetic algorithms, so with each generation, the fitness, I would say, the difference between the model and measured data decreases. Then, so this is it, it's done. Now, let's now look at first of all, we can look at the value of the parameters that were estimated. So if I now go and click on the parameters, for example, if I click on the KD parameter, I'll see the value is changed to 0.806656, which is pretty close to the 0.8 value that I had used to generate the observed data synthetically. and then the initial concentration is 1.023, which is pretty close to the value of 1 that I used to generate the data. I can also look at, so these are the parameters that were estimated. I can now look again at the measured versus modeled graphs. So I just go to the model results. This is my new model prediction based on these parameters that were estimated, and then I also can look at the observed data, and then I can compare them to each other. And here's what we have. This is the best fit we'll get. As I said, you can use the same approach for estimating other parameters, including parameters related to hydraulics or other processes. That the basically way to do it is just like what I did in this example. Thanks for watching, and look for my future videos.